All right, we're ready to define the derivative now. The derivative. So all of that work that we just did about the slope of the tangent line, very important for us to understand the definition of the derivative. So if y equals f of x is a function and a is a number in its domain, then we use the symbol f and that little apostrophe right there. So we say that that's f prime of a. So that's that symbol that I had on Desmos there. So f prime of a to denote the special limit that we just calculated, okay? The limit is h goes to 0, f of a plus h minus f of a over h, okay? So that's that slope of the tangent line, okay? Provided that it exists, of course, okay? So this means that for each number a in its domain, we can assign the special number f prime of a found by calculating that limit. And so many different a values to choose from. This actually is going to define an important new function where you can have all kinds of different input values. And that function is the derivative. So the derivative of the function f at x, so any value x in its domain, is defined as f prime of x equals, and then it's just that limit, but this time it's leaving x alone. We're not plugging in an a value, it leaves it as a variable x. Okay, and we actually work out the algebra on this, and we're going to get an entirely new function that's called the derivative. And so the new function has x involved, rather than just coming out some number like the slope of the tangent line. Okay, and of course, I keep saying provided that this limit exists, and we'll talk about that a little bit later. Okay, like I said, this notation, f prime of x, that's the way that we read this out loud when we say it. So that little apostrophe there, we say it's f prime of x. And f prime of x is a function, okay, very important. We're going to notice that the derivative often has x involved. It often has the variable involved. So it is a function of x. So if x is a value in the domain of f and f prime of x exists, we say that f is differentiable at x, and the process that produces f prime is called differentiation. Okay, so some definitions there for the derivative. The derivative function has several important interpretations, a couple of them that we've talked about already. So the function f prime of x represents the instantaneous rate of change. Okay, so we always want to think about instantaneous rate of change is the derivative, okay, of the function y equals f of x with respect to the variable x. So from now on, the phrase rate of change will refer to instantaneous rate of change. Okay, so whenever you see rate of change, we're now talking about derivative, okay? We're talking about instantaneous rate of change. If they put the word average rate of change, if they put average in front, then you actually just work out the average rate of change formula. Okay, so rate of change is now going to be instantaneous rate of change from now on. The function f prime of x represents the slope of the graph of f of x at any point x. That's going to be the power of the derivative, because we can find out what the derivative is, and then we can plug in values of x. And so we can quickly, like immediately, find out the slope of tangent lines all over the place, wherever we want. So that's why the function f prime of x is so powerful, because you can instantly just start plugging in different values of x equals a into the derivative, and then we get the slope of the tangent line at that point. Very powerful. So we're going to do a few examples of that. Okay. The derivative of a position function gives the velocity function. So we talked about that a little bit in the past. We had a position function, and remember that we were working out the instantaneous rate of change of position was velocity. Okay, because yeah, the change in position over time, that's defined as velocity. And then if you do the derivative of a velocity function, then that's the acceleration function. Because if you have a change in velocity over time, that's called acceleration. Okay, all kinds of good stuff with what the derivative can do for us. Okay, an alternative form of the derivative of a function f at x can be written as this. So f prime of x can be the limit as b approaches x of f of b minus f of x over b minus x. So just an alternative form, and simplifying this is a little bit different than the h version because there is some kind of an extra like factoring and canceling that we might need to do. I always prefer to use the h definition. This is the one that I always prefer to use, okay? But here's an alternative form just for your information. Okay, and then the tangent line to the graph of y equals f of x at the point x1 comma f of x1, or you can think of this as a comma f of a, is given by this equation. And hey, guess what? This is that point slope form that we've been using. So this is y minus y1 equals m, because f prime of x1 is the slope of the tangent line, okay, times x minus x1. Okay, and yeah, if I go back to Desmos, look right here at the bottom. So here's that f prime of a notation that told us what the slope of the tangent line was. And then the graph of the tangent line, yeah, I pretty much just used that. Y minus f of a equals f prime of a times x minus a. Okay, so that was pretty much Desmos, and I was pretty much just using this in Desmos, and it was able to give me, and that, I mean, and that's why it's like so easy to use Desmos to just define all these functions, and then I can get my tangent line wherever I want. Okay, so pretty awesome stuff. Okay, let's do an example now. Let's find the derivative of this function. So f of x equals x squared minus 2x. And then after we find the derivative, then we find and interpret f prime of 3. So for this, if they want the full derivative, that means that we're doing the whole limit process, but we're not plugging in 3 yet. We're going to leave it as an x. Okay, so f prime of x, let's write it out. F prime of x equals, and it's going to be the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so that's just the definition. So now let's write it in. The limit as h approaches 0. So f of x plus h. So we have to be a little careful. This is input squared. So it's going to be x plus h squared. The rest of the function also says minus 2 times the input. So minus 2 times x plus h. Okay, so that's the first part. Then we need minus f of x. Minus, and I usually like to use extra parentheses if there's multiple pieces in there. So minus f of x is just the function itself with x plugged in. So it's just the function itself, x squared minus 2x, all over h. Okay, so let's write this. Limit as h goes to 0. So for the x plus h squared, remember that that has to be FOILed out. So x plus h times x plus h. Let's clean this up a little bit. So that'll be minus 2x minus 2h. Distribute this negative. So that's going to be minus x squared and plus 2x. Okay. Let's keep going. Make sure you keep writing the limit each time until you actually plug in the 0 for the limit. So for this first part, let's FOIL this out. So that's going to be x times x for x squared. Then we have x times h, which is xh, and then times or plus another x times h. So we have plus 2xh. And then continuing to FOIL it out, then we have plus h squared. Okay, then the rest of this stuff, let's see, it looks like we've got, hey, we got some canceling already. So the minus 2x and the plus 2x cancels. And so I'll write out the rest of the stuff. So we have minus 2h minus x squared, and we should have some more canceling all over h. Okay, and then yeah, we know that there should be some kind of canceling, and that's the satisfying part when we know that we're doing it right, when we see that, look, the only thing that's left in the numerator are pieces that have an h involved. Okay, this typically happens when we're dealing with the derivative of some kind of a polynomial. Okay, so we can go ahead and factor an h out of the numerator, and let's see, we've got 2x plus h minus 2, okay, factoring an h out, which then allows us to cancel that h. Okay, let's rewrite this now, 2x plus h minus 2. Okay, now we can do direct substitution, plugging in 0 for h. Now the x has nothing to do with an h, so 2x stays 2x, okay? As h goes to 0, 2x does not change. So that 2x stays the same, that h becomes a 0, and then that minus 2 also does not change. Okay, so h is the only thing that gets affected by all of that. Okay, so we finally get our answer of 2x, and then the 0 isn't there, 2x and minus 2. There it is. That is the derivative. So let's write that again. We have f prime of x. We did all that work and it came out 2x minus 2. So that is the derivative. Okay, and the beautiful thing about doing this whole process without an a value actually plugged in is now that we're done and we have this 2x minus 2, we can plug in any a value we want now. Okay, and so the beautiful part now is f prime of 3. F prime of 3 means that we don't have to do the whole limit process over again. We can find out plugging in 3 right into the derivative function. And so that's 6 minus 2 equals 4. Okay, now it did say interpret. So what does this 4 mean? We found the derivative and we plugged in 3 and it came out 4. What is this 4? Okay, so the slope of the tangent line to the graph of f of x equals x squared minus 2x at x equals 3 is 4. So that's the way that we can interpret this. The slope of the tangent line to the graph of that function at x equals 3 is 4. So we don't even need to graph this, but we already know what the slope of the tangent line would be. Okay. Awesome stuff. I mean, it's so powerful. So I'll make a separate video and we'll do a couple other types of derivatives. So this one's a little bit different with the rational function with x in the denominator. And then we'll do example 4 with a square root. Okay, so good practice. I'll make a separate video to do examples 3 and 4.